Hello students, I am Dr. Kulvinder Singh. Today we are taking some of the numericals from the discipline specific course 9, that is light and matter. All of you are aware of it that the numericals are the backbone of learning of physics. Doing numericals makes the concept more practically clear in your mind, so it's very important to give the importance to the numericals. My advice to you is, while taking this particular lecture, you keep notebook, a pen and a calculator with you so that you can do these numericals yourself. Pause the video whenever it is required, try to solve the numericals and try to match the answer which I am giving. So this will help you to really go into the understanding of the numericals. Now this particular course has 3 units. One is the duality of light and matter, the second unit is on interference and third one is on diffraction. So we are starting with the first unit. So as a first part, let's first of all quickly go through some of the important relations which are from the duality of light and matter. So let's take first of all the photoelectric effect. This photoelectric effect is a very simple process in which you have a material whose work function may be given to you and it is exposed to radiation. Sometimes they give the wavelength or sometimes they give the frequency, and then they talk about the electron which is coming out of it. So the basic equation, which is known as the Einstein's photoelectric equation, is written as h nu is equals to phi plus half m v max square. Let's recognize all these things. H is a Planck's constant, nu is the frequency of the radiation, this is the work function, and this is the maximum energy, that is half mv max square, maximum energy of the electron which comes out from it, which we call as photoelectron. Now you may have this form of the equation or you can modify this form in this way. For example, instead of frequency they may give you the wavelength, so you can change it to h nu to hc by lambda. C is the velocity of light in free space and lambda is the wavelength. You can also change the expression for the work function, and that can be hc by lambda 0 or sometimes is written as h nu 0. Here lambda 0 is the threshold wavelength, that means radiation of wavelength higher than lambda 0 cannot do the photoelectric effect. Nu 0 is called the threshold frequency, so radiation of the frequency less than threshold frequency cannot do the photoelectric effect. So this may be the information given to you, so you please check and modify your equation. The point number C, that is regarding the half mv max square, that is the maximum kinetic energy. Instead of having this form, you may be given the information for the stopping potential. This is the maximum kinetic energy and this is the electrical potential energy required to stop them. So Vs is the stopping potential, that is the potential which is required to make the maximum energy photoelectrons to stay in the matter. So you may have these variations in this particular equation. Students, in examination you are allowed to use calculator, so it's not very difficult to do the calculation. However, there are certain quick tips to remember. Let me just share one of the tips with you. If you are given the wavelength of photon, say 1000 angstrom, and you have to convert it into energy in the unit of electron volt. You may use this relation to get it, but there is a pre-calculated value. The 1000 angstrom is equivalent to 12.43 electron volt. You can check it yourself. Put the value of 1000 angstrom for wavelength, use and convert this energy into the electron volt. You will find this comes out to be 12.43 electron volt. However, there is one important point to remember. If you are given the wavelength in the multiple of 1000 angstrom, say for example you are given wavelength equal to 2300 angstrom, that means your multiple now is 2.3. So you should divide this number to get the energy. Here it is in multiple and here it is in division. This is simply because the wavelength is in the denominator. So more wavelength means less energy. So whenever you have a multiple of 1000, you can directly convert this. But I'll advise you to use this particular relation to check your answers quickly, right? But better to solve it using a calculator. That is the requirement of the examination. So with this we come to the next point, and that is the Compton effect. So students, let's take the next point, that is the Compton effect. In this effect, a photon is interacting with an electron in a matter. These electrons in the matter, they are not in rest position, but their velocity is very, very small as compared to the velocity of light. So we practically assume them to be in the rest position. So what we have this type of situation. We have an electron and a photon is coming to it. They make collision, that is the elastic collision, and we find the photon takes a path like this, and say the electron moves in this direction. This particular angle is called the scattering angle phi. If the wavelength of the incoming photon is lambda, say initial value lambda 0, and the wavelength here is lambda after interaction, then this lambda minus lambda 0 is given as h by m of the electron c 1 minus cos of phi. This is basically is called the Compton equation. In this particular quantity, h m0c is called the Compton constant, and the value of the Compton constant is 2.426 10 to the power minus 12 meter. But in this particular relation, we have to keep one thing in mind, that this angle, scattering angle, is for the photon. One more thing, always there is a increment in the wavelength. The maximum change, or you can say Compton shift, is for that photon which retraces the path. In that case, the angle phi, this angle, becomes 180 degree, and cos 180 degree is minus 1. So maximum Compton shift, that is the maximum shift of the wavelength, is twice the value h by m0c. Right? That is twice of this value is the maximum possible change in the wavelength which we can expect from the Compton scattering experiment. Now take the third point, that is the duality of the light and matter. For this, the main equation is the de Broglie equation. That is, the de Broglie wavelength is equals to the Planck's constant divided by the linear momentum of the particle, or maybe the photon. This particular equation is applicable both for matter as well as for radiation. Now, as a special case, you may find sometime we talk about a particle, say electron, which is accelerated by a potential difference V. Obviously, in this condition, this electron will acquire energy which is equals to E into V, and you can relate it to the linear momentum by the equation P square by twice of m, where P is the linear momentum. So the momentum is given as under root of 2m, that is mass of the electron, E into V. Obviously, the de Broglie equation therefore is equal to h divided by under root of 2me multiplied by under root of V in the denominator. Now this de Broglie wavelength can simplified as 12.27 under root of V in the unit of angstrom. This is a pre-calculated equation. Once again, you can make use of this to find out the correctness of your answer quickly. But this is for the electron only. Had it been a case of a proton, then you should use the mass of the proton to calculate out the momentum and then the de Broglie equation. So let's take the fourth point, and that is the wave packet. All you know that wave packet is basically a superposition of large number of the harmonic waves. Such a wave packet possesses two velocities. We call it as a phase velocity, which normally is written as omega by k, where omega is the angular frequency 2 pi nu and k is the propagation constant, which is 2 pi by lambda. Wave packet as a whole is having a velocity, we call it as a group velocity, and that is given by a relation d omega by dk. Group velocity is related to the phase velocity, and that is group velocity is equals to the phase velocity plus the propagation constant, the derivative of the phase velocity divided by dk. There are a number of the versions of this relation. So if change is required, you can make use of these relations to get the change. So these are some of the quick relations from this unit, and now we are starting the numericals. So let's take the first numerical. So let's take the first numerical. Two things are given to you. One, the wavelength of the light, that is 650 nanometer, and the power, that is equals to half milliwatt. And we are required to find out the number of the photons produced per unit time. Now in such a case, we have to look first of all the expression for power. Power is the energy per unit time, and energy, when we talk about the radiation in terms of photon, can be written as number of the photons, and each photon possesses energy which is equals to h nu. So the total energy of the radiation can be written as the number of photons multiplied by the energy of one single photon. So obviously E equals to n h nu divided by T. From here, this n by T can be given as the power divided by h nu. Since wavelength is given to us, so we can put h nu as c by lambda. Lambda will come in the numerator. So if you calculate n by t, this is going to be the power, which is equals to 5 into 10 to the power minus 4, because it is milliwatt, multiplied by the wavelength. The wavelength is 650 nanometer. So this is 650 into 10 to the power minus 9, and then divided by the Planck's constant, which is 6.63, 10 to the power minus 34, multiplied by velocity of light in free space, that is 10 to the power 8. Now if you calculate, you will get the answer for this as 1.63 10 to the power 15 photons per unit time, that is second. So this is the answer for your first numerical. So now let's take the second numerical. We are given that there are two radiations, one of wavelength lambda 1 equal to 600 nanometer and another one of wavelength 400 nanometer. The stopping potential found for the first case is 1 volt and for the second case is 2 volt. Now the basic equation is Albert Einstein's photoelectric equation, that is equals to h nu equal to phi plus half mv max square. But we need to modify it because we are given the wavelength. So let's write this as hc by lambda phi as it is, plus instead of half mv max square we'll write this as E into Vs. So for the first case you write the same equation, and for the second case, and let's take the subtraction of the two. hc by lambda 1 is equals to phi plus EVS1. This is for the first case. Similarly, we have hc by lambda 2 is equals to phi plus EVS2. Note, I kept the work function same because the material is same. So let's do the subtraction of the equation 2, right, by the equation 1, and we write equation 2 minus equation 1 as hc 1 by lambda 2 minus 1 by lambda 1 is equals to E Vs2 minus Vs1. So you can write the Planck's constant as E Vs2 minus Vs1 divided by 1 by lambda 2 minus 1 by lambda 1. Now let's put the numerical values for it. So Planck's constant therefore is equals to 1.6 into 10 to the power minus 19. The Vs2 is 2 volt and this is 1. 2 minus 1 divided by, this is C also. This C will come. C come along with this. So do the correction for it. C, that is equals to 3 into 10 to the power 8 divided by 1 by lambda 2. Lambda 2 is given 400 nanometer, which means 4 into 10 to the power minus 7 minus, the second one is 6. 6 into 10 to the power minus 7. Now when you are handling this type of the equations, I'll advise you to handle the power separately and the numerical value separately. That will help you to get the answer fast. So H is going to be 1.6 divided by, so you can take out this 10 to the power minus 7 in the numerator, that becomes 10 to the power plus 7, 10 to the power 8, that is 10 to the power 15, and when you bring it up, obviously this positive power will become negative. So 19 and 15, that will give you 10 to the power minus 34. Rest is a numerical value 1 by 4 minus 1 by 6. Obviously everything is done in SI unit, so Planck's constant will be in the joule second, that is SI unit of 8. And if you simplify, you will get the answer for the Planck's constant. You can just check it yourself. Just give a pause to this and try to calculate it out, and that comes out to be 6.4 10 to the power minus 34 joule second. So this is your answer. So let's take the third numerical. It is very simple. Given that the threshold frequency is 1.4 10 to the power 15 Hertz and the frequency of radiation is 2 into 10 to the power 15 Hertz, and we are required to find out the maximum energy of the photoelectron. So let's use the photoelectric equation H nu is equals to phi plus E max. So E max therefore comes out to be H nu minus the work function. Just modify it a bit, taking the work function as H nu 0 and this is H nu minus nu 0. So here is our answer. H max is equals to 6.63 10 to the power minus 34 2 minus 1.4 into 10 to the power 15, and since everything is in SI system, so unit is going to be joule. So if you simplify it, this is equals to 6.63 10 to the power minus 34 multiplied by 0.6 into 10 to the power 15 joule. And if you simplify, this comes out to be E max equals to 3.98 into 10 to the power minus 19 joule. So this is our answer. Sometime question demands that you express it in electron volt. So to convert this energy into electron volt, so you can do like this. E max in terms of electron volt can be written as 3.98 into 10 to the power minus 19, that is taken in SI system, divided by the charge of electron, that is 1.6 10 to the power minus 19, and if you do that, this will come out to be 2.48 electron volt. If they demand you give it in this unit, or if they simply ask you to calculate the maximum energy, even this is sufficient. So let's take the fourth numerical, and given in this numerical is the wavelength which is 4000 angstrom and stopping potential is 1.5 volt. We are asked to find out the work function. Once again we are using the photoelectric equation H nu is equals to phi plus E into Vs. Instead of maximum kinetic energy I have written E into Vs because we are given the stopping potential. So obviously phi now is given as H nu minus E into Vs. Since wavelength is given to us, so we can change this H nu as Hc by lambda minus E into Vs. Now this equation is fit for putting a numerical values to find out the work function. So as a first part, the work function now is equals to 6.63 10 to the power minus 34, that is the Planck's constant, multiplied by 3 into 10 to the power 8, that is the velocity of light in free space, and 4000 angstrom is 4 into 10 to the power minus 7 meter. Subtracting 1.6 10 to the power minus 19, the charge of the electron, and the stopping potential is 1.5 volt. All quantities are in SI system, so obviously the answer we are going to get, that is in joule. So if you solve it, you will find, you will get the answer 2.57 into 10 to the power minus 19 joule. You please check it yourself. This is the answer for the first part. The second part, he demands that what is the maximum wavelength for which the photoelectric effect will occur. Obviously, you have to modify the expression for the work function, which is equals to Hc by lambda 0. This is called the threshold wavelength. As I told you, that if you have a wavelength more than this, you are not going to get the photoelectric effect. So this is the maximum possible value of the wavelength for which the photoelectric effect will occur. So obviously this is equals to Hc by phi. So you can make use of the value we have obtained to find it out. 6.63 10 to the power minus 34 multiplied by C, that is 3 into 10 to the power 8, and the value we have obtained here is 2.57 into 10 to the power minus 19. So this comes out to be in meter. So if you simplify it, you will get the wavelength as 7.74 into 10 to the power minus 7 meter, or you can write this as 7740 angstrom. So this is the answer for the second part of the question number 4. So let's take the fifth question now. In this question, we are given a graph between the kinetic energy maximum and the frequency. And it is a straight line, as you can see. Now, you are asked to find out the work function as well as the Planck's constant. So let's visit the photoelectric equation once again. It says that the h nu is equals to work function plus the maximum kinetic energy. So if I modify it a bit, writing it in this way, the kinetic energy maximum is equals to h nu minus of the work function. This actually represents a straight line equation. Let's compare it with standard equation for the straight line, where m is the slope. Look, on x-axis we have frequency, on y-axis we have kinetic energy maximum. So obviously work function is nothing but is the negative, you can say, y-intercept of this straight line. So you have two ways to find out the work function. First of all, you may extend this line and to find out where it meets. Or another simple way to get it, the work function can be given as h nu 0, where nu 0 is nothing but the threshold frequency. You can notice from here the threshold frequency as seen from the graph is 2 into 10 to the power 14 Hertz. So you can calculate work function straight away as 6.63 10 to the power minus 34 multiplied by the frequency 2 into 10 to the power 14 Hertz multiplied by the Planck's constant. And if you simplify, this comes out to be, the work function will come out to be 1.33 into 10 to the power minus 19 joule. This is the answer for the first part. Now the second part is nothing but the slope of this straight line. The slope is nothing but is delta y divided by delta x. Delta y, you take the entire line, so this goes from 0 to the value 5. That means this is 5, but this is given in electron volt. So one has to convert this to 10 to the power minus 19 in joule. And delta x, that is from 2 to 14, that means this is 12 into 10 to the power 14, that is the unit given here, this much, and this is nothing but is in joule second. If you simplify this, this will come out to be 6.66 10 to the power minus 34 joule second. The value, however, is not close to the exact value, but whatever is coming out from the graph, you mention that. So this is the numerical number 5. So let's take the sixth question. In this question, wavelength of the light is given 200 nanometer. The work function is 4 electron volt. and the electrons so obtained are passed through a magnetic field in a perpendicular direction, and as we know that if charged particle is moving through a uniform magnetic field, they take a circular path. So they asked us to find out the radius. So radius of the circular path we have to obtain, which is going to be maximum for those electrons which have the maximum velocity. So let's calculate first of all the maximum velocity from the relation h nu is equals to work function plus half m v max square. So from here we can write v max is equals to h nu minus work function whole multiplied by 2 divided by m under root. Now if you put the values here, this is 2, 6.63 10 to the power minus 34 multiplied by the frequency. The frequency can be written as 3 into 10 to the power 8, that is C, divided by the wavelength, which is 2 into 10 to the power minus 7. I have converted from nanometer to meter, and then the work function to be subtracted, but it is given in 4 electron volt. So one has to write this as 4 multiplied by 1.610 to the power minus 19, and then whole of it is to be divided by the mass of the electron, which is 9.110 to the power minus 31 kg. Then you take the under root of it to find out the maximum velocity. My calculation gives me the value 8.83 10 to the power 5 meter per second. You just pause the video and calculate it to check, is it okay? There may be a small difference, that depends how you are doing the use of calculator and how much significant figure you are keeping in it. So this is 8.83 10 to the power 5 meter per second from my calculation. And the radius, as we know, is given by the formula mv divided by qb. That is the general formula to find out the radius of curvature of the particle which is entering into the magnetic field in a normal direction. So for our case, the R max is going to be m v max divided by the electronic charge, because we are talking about the electron, and the magnetic field we applied. So this is going to be 9.1 into 10 to the power minus 31, and V max already we have calculated. So that is 8.83 10 to the power 5 meter per second divided by the electronic charge 1.6 10 to the power minus 19, and the magnetic field we have is 0.5 Tesla. So if you simplify this, this comes out to be, radius will come out to be nearly equal to 1.0 10 to the power minus 5 of meter. So this is our answer for the question number 6. Now let's take the 7th question. 7th question is on Compton effect. The incident photon has a wavelength of 0.124 nanometer, and there is an increase of 1% in the wavelength. That means the wavelength now will become lambda 0 plus 1% of the lambda 0. They asked us to find out the scattering angle and the energy loss in the process. Let's calculate first of all what is the scattering angle. Write the Compton relation, that is lambda minus lambda 0 is equals to h divided by m of electron c 1 minus cos of phi. This constant h divided by m of c has a value 2.426 10 to the power minus 12 meter, and we can make use of this directly. So in order to find out this, we can write the change, that is 1 0.01 of lambda 0 minus lambda 0 is equals to 2.426 10 to the power minus 12, 1 minus cos of phi. So you take it out, 1 minus cos of phi, this will come out to be 1.01 minus of this will give you 0.01 of lambda 0, and lambda 0 he has given 0.124 nanometer, that means 10 to the power minus 9. This is the value of change we have. Then divided it by 2.426 10 to the power minus 12, and from here we can write cos of phi is equals to 1 minus the value which we get from here, and this is equal to say 0.01 into 0.124 divided by 2.426 10 to the power minus 12, when will come in the numerator will become 10 to the power 3, and if you simplify you will get the value as 1 minus 0.51, and if you solve it, this is equals to 0.49, and if you solve it for phi, you will get the value as 60.66 degree. So this is the answer for the first value required in this question. Now the second point, he is asking to find out the energy loss. The energy of the photon initially was hc by lambda 0, and the energy of the photon after scattering will become hc by lambda. So this is the loss of energy which the photon suffers. To calculate it, this delta E, you take it this way, 6, take this hc out, and it is equals to 1 by lambda 0 minus 1 by lambda. So this is 6.63 10 to the power minus 34. Putting the value of the C, that is 3 into 10 to the power 8. 1 by the wavelength. Wavelength given is equals to 0.124 nanometer, 10 to the power minus 19, and lambda is equals to 1.01 multiplied by 0.124 10 to the power minus 19, and this comes out to be, the delta E comes out to be, from my calculation, this is 1.59 into 10 to the power minus 15 joule. So this is answer for the second part of this question. So students, now let's take the 8th question, which is again on the Compton effect. What has been given to us, that the initial wavelength of the photon is 0.07 nanometer and the scattering angle is 120 degree. And the question demands that we have to calculate the momentum given to the electron. So let's first of all understand the process. When photon comes and strikes the electron, obviously momentum conservation takes place, energy conservation takes place, because we assume this type of collision to be elastic collision. Now there is a change in the wavelength of the photon and we have the formula for it. But this way we can calculate the change in wavelength of the photon. Once we know this, we can find out the change in the energy of the photon. Now, according to the conservation of energy, if there is a loss of energy by the photon, obviously there is a gain of the energy of the electron. Now, once we know the loss in energy of the photon, that will be the gain in energy of the electron. From there we can work out the momentum of the electron. So our process is going to be, first of all we'll try to find out the wavelength. We are given lambda 0, we'll come to the wavelength. From the wavelength we'll come to the change of energy, or rather energy loss of the photon. But the loss of the photon is a gain of the energy of electron, that is a change in energy of the electron, and from there we come to the momentum of the electron. So this is going to be the process by which we are going to solve this problem. So once the path is clear to you, rest is simple mathematics. Let's calculate first of all the wavelength. The wavelength is going to be lambda 0, that is h by me of c, 1 minus cos of phi. So this is 7 into 10 to the power minus 9, and 2 will make it minus 11, which I prefer to write as 70 into 10 to the power minus 12. Why I am doing so? Because this Compton constant is 2.426 into 10 to the power minus 12. So there will be a match with the power, so it becomes a bit easy for me to do. This is plus, this is Compton constant, 1 minus cos of 120 degree is minus half, which will make it plus half. So the things becomes bit easier. If you simplify this, I get the value that is equals to 73.639 10 to the power minus 12 of meter. This is my first step. That means I have reached to this level. Then we calculate the energy loss as we done in the previous question, which is basically is hc by lambda 0 minus hc by lambda. This I can write as hc lambda 0 lambda minus lambda 0, and 6.63 10 to the power minus 34, 3 into 10 to the power 8, that is the velocity of light, and the difference we have worked out is 3.639 into 10 to the power minus 12 divided by 70 multiplied by 73.639 10 to the power minus 12 and 10 to the power minus 12 coming from lambda and from lambda 0. So if you simplify this, the energy loss which we have obtained is 1.4 into 10 to the power minus 12 of joule. This is the energy loss. This is the step. Up to this we have done. And same is going to be the energy of the electron. The same value. So rest to find out the momentum of the photon. And the momentum of the photon can be worked out since electron moves. So the kinetic energy is the kinetic energy which is lost by the photon, and that is 1.4 into 10 to the power minus 12 of joule. So momentum is twice of m, the mass of electron 9.1 10 to the power minus 31 multiplied by 1.4 into 10 to the power minus 12 under root. And this way, if you calculate the momentum, and momentum comes out to be 1.596 into 10 to the power minus 21 Newton second. So this is the answer for the question number 8. Now it's slightly bit lengthy one, but if you follow the route, you are able to get the answer. Sometimes students do an error in it. What they do is, once they calculate lambda, they try to work out the change in momentum of the photon. And it comes immediately in mind that there is a momentum conservation. So if there is a loss or change of momentum of the photon, it's going to be the gain of the momentum of the electron. But story is not like this. Since momentum is a vector quantity, we have to deal with the vector form of the momentum. It is not a one-dimensional collision. It is basically a two-dimensional collision. So I advise you not to use the conservation of momentum, rather use the conservation of kinetic energy in this particular type of question. So students, let's take the 9th question now. This is on the duality of matter. It's given that there is a neutron which is moving with energy, and the energy given is 1 giga electron volt. But in the question, they have mentioned the rest mass of the neutron, which is 939 MeV. And it is clearly mentioned that it is not non-relativistic thing. We have to take the relativistic concept into the picture. Normally when we write the kinetic energy, we write the kinetic energy as P square by 2m. But this relation is a classical equation. It is not a relativistic equation. In the chapter of relativity, you come across this relation, that is E square is equals to Pc square plus m0 c square whole square. Here P is the linear momentum. We are not going to use this equation for calculation of the momentum. Obviously we will use this equation to calculate the momentum, and then we can go for finding out the de Broglie wavelength. So this is the point in this particular question which you have to care. Now from this relation, this first of all energy which is 1 giga electron volt means that 1 into 10 to the power 9, that is the meaning of the giga. Electron volt means 1.6 10 to the power minus 19, and that much of joule. So this comes out to be 1.6 into 10 to the power minus 10 of joule. Similarly, the rest mass energy of the neutron is 939. Mega means 10 to the power 6. Electron volt means 1.6 into 10 to the power minus 19 joule. So this is the 1.5024 into 10 to the power minus 10 of joule. So once you calculate these energies, it will become easy for us to find out the momentum. So the Pc square is going to be the energy, that is 1.6 into 10 to the power minus 10 whole square minus 1.5024, although there is no need to write this, but let's keep it 10 to the power minus 10, that is m0 c square. There is the rest mass energy whole square, and from here you can calculate the momentum, and the momentum calculation will come to a relation, that is 1.83 10 to the power minus 19 kilogram meter per second or Newton second. So use this relation to find out the momentum. Rest is simple. The de Broglie wavelength can be given as h by p, 6.63 10 to the power minus 34. The momentum we have worked out in equation number 3, that is 1.83 10 to the power minus 19, and that will come out to be 3.62 into 10 to the power minus 15 of meter. So this is the answer of this question. But here we have to use the relativistic equation to find out the momentum. So now let's take the 10th question. In this question, we have to calculate the de Broglie wavelength of an electron, but there are two velocities given to us. One is 10 to the power 5 meter per second and another one is 10 to the power 8 meter per second. We have to be careful in this case because when it is 10 to the power 5 meter per second, the relativistic mass of the electron is very close to the rest mass of the electron, that is 9.1 10 to the power minus 31 kg. So you can directly calculate the momentum by taking the rest mass. But when it comes to the higher velocity, that is 10 to the power 8, which is quite close to the velocity of light, we cannot ignore the relativistic mass of the electron. So there is an increment in the mass of the electron which we have to calculate. So let's do the calculation. For the first case, the de Broglie wavelength is h by the rest mass multiplied by the velocity, and this is equals to 6.63 10 to the power minus 34 divided by 9.1 into 10 to the power minus 31 kg multiplied by the velocity, which is 10 to the power 5. And if you calculate this, this comes out to be 7.28 into 10 to the power minus 9 of meter. This is the de Broglie wavelength for the first case. But when it comes to the second one, we have to do little bit calculation to find out the relativistic mass, which is equals to m0 under root of 1 minus v square by c square. So if I calculate this, m0, this is under root of 1 minus v square. V is 10 to the power 8. So this comes out to be 1 by 9. 3 square, that gives you 1 by 9. And this is 8 by 9, or you can say this is 3 under root of 8 m0. So this way we have to calculate the mass, and this is 3 divided by under root 8, mass 9.1 10 to the power minus 31 kg, and this comes out to be 9.652 into 10 to the power minus 31 kg. There is increment in the mass, you can notice. Rest is simple as we calculate de Broglie wavelength is equals to h by p. Now in the second situation, this is h divided by, the momentum comes out to be now 9.652 10 to the power minus 31 multiplied by 10 to the power 8. And this way the wavelength is 6.869 10 to the power minus 12 of meter. So you can notice that there is a drastic difference in the values, and this is 10 to the power 9 meter, but because of the increment of the mass, there is an increase in the momentum of the electron, and therefore there is a decrease in the wavelength of the electron.